Hello, everyone. Thanks for joining us in this thermal analysis webinar. We appreciate your time. My name is Don DePietro. I'm the Vice President of Product Management and Applications here at Canon Instrument Company. I'm going to moderate the presentation. I'll say at the outset, we will make a link available to you if you want to review certain sections of this presentation at a later date. But before I introduce the presenter, I just want to let you know this will take approximately 45 minutes. We'll then have about 10 minutes at the end for questions. So that way we can finish before the end of the hour. We're going to mute your microphones so we don't have any distractions. But if you have questions, please, as you go, type them into the Q&A section. You should see a Q&A button at the top of your screen. And at the end, we're going to relay them to Terry and we'll get them answered. If for some reason we go to 12 noon and we have too many questions, we will get back to you and answer your individual questions. Dr. Terry Chen earned her PhD at Sun Yat-sen University in China. She's focused on polymer synthesis and material engineering. In 1999, she moved to the States. She worked as a postdoc at the University of Maryland and became a research assistant professor there. Prior to joining Canon, Terry and I both worked at TA Instruments. She was a principal application scientist and a technical leader. She's produced a wide range of polymer-related webinars on adhesives, thermoplastics, thermosetting polymers, sustainability. She's a board member and technical program chair for the SPE and their Applied Rheology Division, Society of Plastics Engineers. She has over 50 publications in peer-reviewed journals and two U.S. patents. Terry will present on the subject of enhancing your understanding of polymers using thermal analysis. I'll turn it over to Terry. Thank you.
All right. Thank you very much for your introduction. Good morning, everybody. My name is Terry Chen, and welcome to join Canon Instruments webinar today. Our today's topic is on enhance your understanding of polymer materials with thermal analysis. Before we start talking about thermal analysis, I would like to spend a couple minutes introducing Canon Instrument, who we are and what do we do. Canon Instrument Company was first founded in 1938. At that time, Canon was a startup company from Penn State University. The founder of the company was Dr. Michael Cannon, who was the original designer for the first version of Canon Fensky glass viscometer. Since then, Canon has become the world leader of automated glass capillary viscometers and has expanded the business into the manufacturing of other type of automated viscometers and rheometers. We also offer other instruments for measure different physical properties. Canon is a global supplier for standard reference materials for many physical properties. One of our major standard products is the Canon viscosity standard. Many of you may have already seen those Canon viscosity standard bottles in many chemistry and analytical labs. Our products are sold anywhere worldwide, and we're supported by a network of distributors and partners. Starting this year in 2024, Canon and Hitachi become partners. Canon will help Hitachi High-Tech to grow their thermal analysis business in the United States. From now on, Canon is expected to provide to our customers with a more comprehensive characterization needs. So the history of Hitachi thermal analysis product traces back to the old time of 1970s and 1980s. Some of you may still remember the name of an old thermal instrument company called Seiko Instruments. Back in the old time, Seiko was one of the world leaders who manufactured different models of thermal calorimeters. In 2013, Seiko joined the big family of Hitachi High-Tech. Ever since then, Hitachi has been investing more resources on developing new and high-end thermal analysis instruments. In 2019, Hitachi first launched their new model simultaneous DSC and TGA analysis instrument with the real view camera view system. 2 years later, they released their new generation DSC instrument, which has the world-class best baseline stability and sensitivity. Also, just last year, Hitachi again introduced their new model dynamic mechanical analyzer, the DMA instrument. As we can see, over the years, Hitachi has been actively introducing their new model thermal instruments and new technologies to the world. Hitachi High-Tech headquarters is located in Oyama, Japan. They have over 70 dedicated thermal analysis employees, including manufacturing, R&D engineering, service, and applications. They have installed and sold over 10,000 thermal instruments worldwide, including in the United States. Hitachi High-Tech thermal business has been very successful in many Asian countries, which including Japan, China, Singapore, and India. Their thermal instruments are also popular in European countries, such as in UK and Germany. In the United States, Hitachi has its own thermal applications lab located in Dallas, Texas. They also have their own local service and support team. This year, Hitachi is working with Canon and is expecting to further grow their thermal analysis business in the United States. So therefore, in our today's webinar, I am happy to introduce to our audience the Hitachi thermal analysis techniques. Also, I'm going to spend the majority of our time talking about the application of thermal analysis in polymer industry. How can we use thermal characterizations to help polymer chemists and polymer engineers with their new product development and polymer processing? Thermal analysis techniques has been widely used in polymer industries. They can help identify polymer resins, quantify impurities, provide compositional analysis, and also troubleshooting any production issues. These thermal instruments are commonly used as laboratory QA/QC tools, as well as for high-level research need in R&D departments. Many of those characterization methods are following the ASTM, ISO, or other industry regulations. So in our today's talk, I would like to specifically focus on discussing the application of 4 thermal analysis techniques: the DSC, the TGA or STA, TMA, and also DMA. First of all, let us talk about differential scanning calorimetry. DSC is probably one of the most popularly used calorimeters in polymer industries. A DSC instrument measures the differences in heat flow rate between a sample and an inert reference. It can perform the measurements as a function of temperature or time. Through observing the endothermic or exothermic activities of the sample, a DSC scan can measure a polymer sample's glass transition, crystallization, crystal melting, polymorphic transitions, and heat capacity. The DSC technique can also be used to study thermoset curing, measure oxidative stability of a polymer resin, and also help identify impurities in recycled polymer PCRs. Hitachi new model Next DSC provides to their users with the excellent baseline stability. This helps users to build their confidence in data accuracy and repeatability. Hitachi DSC is equipped with a 4-finger design auto sampler, which allows up to 50 samples automatically loaded at the same time. The auto sampler provides the most reliable automation. It saves your sample loading time. For sample preparation, Hitachi provides users with an automated pan sealer, which ensures the best sample preparation reproducibility. One of the best technical highlights on Hitachi DSC is on their flexible and interchangeable dual cooling system. Most of the DSC users know that for a typical electrical cooling system on a DSC can cool the samples down from -40 to -90 degrees C, depending on which model do you use. But if a user occasionally needs to cool the sample down to liquid nitrogen temperature, which is -150 degrees C, he or she may have to end up purchase an additional second DSC in order to do so, which could cost more money and also take over some more lab bench space. Hitachi DSC allows both the LN2 and electrical cooling system installed on the same DSC unit. Users can select to use their desired cooling system through a simple switch in the software. Another technical highlight is this fully integrated real-view polarized microscope system. This microscope provides a unique visual analysis capability on samples during a DSC measurement. Here is a fun application example showing the usefulness of this real-view system. We put a picture underneath a piece of polymer sample. Because the polymer is partially crystallized, it looks black underneath the polarized microscope. However, as we conduct a heating test on this sample, so let me play the video here. When the temperature passes its crystal melting temperature, the polymer turns clear. Now we can see through. Now we see the picture underneath the polymer is a picture of Godzilla. Then, as we cool the sample down, polymer recrystallizes and turns black again. Actually, there are many useful applications of having this polarized microscope visual capability. I will elaborate and discuss more practical examples in my later section. The second thermal analysis technique I would like to talk about is the TGA, thermogravimetric analysis. Hitachi provides with their users a STA instrument, which is capable of doing a simultaneous DSC and TGA measurement. In addition to monitor the endothermic or exothermic activities of the sample, the STA technique is mainly used to measure the mass change of a sample through heating. For example, it can measure moisture or residual solvent content, monitor sample decomposition, and calculate decomposition kinetics, measure thermal and oxidative stability. It is also commonly used for compositional analysis for filled polymer composite. The STA is also a good high-temperature DSC, which can measure crystallization, crystal melting, and crystal phase transition. Hitachi STA instruments has this dual beam horizontal design, which has low buoyancy influence with excellent baseline stability. This allows users to be able to detect the smallest weight change even from the smallest sample size. The four-finger auto sampler design provides fully automation and reliability on sample loading. Hitachi STA has up to 4 gas flow controllers, which is easy to switch and allow mixture gas purge. Their efficient gas flow path is perfect for testing oxygen-sensitive samples. Also, the interchangeable furnace and furnace tube provide a wide temperature range and allow sample being tested under corrosive gas environment. Hitachi STA is also integrated with a real-view camera system. One application example for this feature is that it can perform color analysis. You can monitor at what temperature your sample gets oxidized and turns yellow. The third thermal analysis technique I would like to introduce here is the thermomechanical analysis. A TMA instrument is mainly used to measure a sample's dimension stability as a function of time, temperature, humidity, or under a certain force or displacement. TMA is commonly used to measure a sample's coefficient of thermal expansion, the CTE. It can also measure thermal shrinkage, softening point, and glass transition temperature. A TMA is also capable of performing some basic DMA mode testing, such as dynamic temperature ramp, stress relaxation, or creep. Hitachi TMA provide to their users with the highest force range up to 5.8 Newton. This benefit for testing large and stiffer samples and also good for DMA mode testing. In addition to high force, this instrument also allows large sample size, which provides the best sensitivity for testing samples with low CTEs. Hitachi TMA instrument is equipped with varieties of different type of testing probes that allows sample being tested under different mode, such as tension, compression, bending, or penetration. And this instrument offers 4 different types of cooling systems, which provide a wide range of temperature and flexibility for users to switch. The last thermal analysis technique I would like to introduce is the dynamic mechanical analysis instrument, the DMA. A DMA measures the mechanical and viscoelastic properties of a material. The measurement can be performed as a function of time, temperature, frequency, or as at a specific applied stress or strain. The DMA technique is mainly used to measure samples' stiffness, which is described as the modulus, and also measure samples' elasticity, which is described as the damping factor, the tangent delta. DMA is the most sensitive instrument to measure a polymer's glass transition temperature, as well as any subambient beta-gamma transitions. A DMA can be used as a mini instrument to perform a basic stress-strain test to measure Young's modulus. It can also perform some transient measurements, such as creep recovery or stress relaxation. Hitachi new model DMA was just released last year in 2023. This DMA has a completely new motor design with a wide force range up to 20 Newton. This allows users to measure any type of samples from soft to stiff. The instrument is equipped with all measuring clamp options, which allow samples to be tested under different deformation modes, such as tension, bending, compression, or shear. Hitachi DMA provides users with 3 different cooling options, which gives a wide range of temperature control. The software offers Wizard for sample handling, clamp calibration, and experimental setup, which is perfect for new users. Hitachi DMA is also equipped with a real-view camera system that allow users to be able to see the sample during the measurement. Before we jump into discuss applications, I would like to also highlight some of the good features on Hitachi Nexter software. First of all, the Nexter software is designed for both instrument control and data analysis on all 4 of their thermal analysis instruments. Nexter software has built-in Wizard with calibrations, sample handling, and experimental setup. It also has this simple test mode setup, which is perfect for new users. In addition, Hitachi software has this built-in ASTM, ISO, and other industry standard method, which allows users to easily follow the industry regulation. This software is easy to use and self-learn. In this next section, I would like to discuss some practical application case studies on how to use the thermal analysis techniques to help with polymer product development and polymer processing. Like I said earlier, thermal analysis techniques are so widely used in polymer industries. People use thermal analysis to identify their polymer resins, quantify impurities, evaluate product crystallinity and crystal melting, measure mechanical properties, and also troubleshooting production issues. First of all, let's talk about DSC applications. DSC is probably the most commonly used thermal instruments in polymer characterizations. DSC analysis is typically used for identifying the raw material. A simple DSC temperature scan can tell you if this polymer resin is a polyethylene, polypropylene, or if it is a PET resin. DSC identify polymer IDs based on the differences in their glass transition and melting temperature. Even within the same type of polymer, for example, polyethylene, the DSC measurement can also sensitively differentiate the differences in different grades. Here is an example of using DSC to differentiate the different grades of polyethylene resins. LDPE, low-density polyethylene, mostly contains long-chain branching structure. Therefore, they usually have relatively lower density. Figure 1 shows two different grades of LDPE resin with different density. The measurement results show that they have their crystals melt at different temperatures. The higher the density, the higher the melting temperature. This same trend can also be observed in the case of HDPE resin. High-density polyethylene resins are mostly linear. Therefore, they usually have higher density with higher crystallinity. Their crystal meltings are also observed at higher temperatures compared to LDPE resins. So figure 2 shows that for HDPE resins, higher density also leads to a higher melting. In polyolefin industries, this DSC measurement is commonly used to identify different grades of polyethylene and polypropylene resins. DSC technique is also commonly used in polymer recycling for the purpose of identify and quantify impurities. So in this case study, from a DSC temperature scan, we observed a big crystal melting at temperature around 130 degrees C, which correlates to the melting of HDPE. From these results, we can say that for this particular batch of PCR resin, it mostly contains HDPE. However, at temperature around 160 degrees C, we can also identify another small melting peak, which correlates to the melting of PP. So with integrating the melting enthalpy and compared to the melting enthalpy of a pure PP, we can get a reasonable estimation to find out how much PP contamination there is in this particular batch of PCR. DSC is commonly used to determine the oxidative stability of a polymer. There are some industry standards, such as ASTM, ISO, or DIN standards. They all provide specific instructions of using DSC to identify the OIT of polymers. OIT means oxidation induction time. This is a standard DSC test method to study the time of a polymer to start getting oxidized at a certain temperature. The figure on the left side shows the OIT test of 3 different grades of polyethylene resins. After equilibrated at temperature of 250 degrees C, we switched to use air purge, introducing oxygen into the DSC furnace. So the OIT time is defined as the onset point at the heat flow curve. So from this comparison data, we can see that sample A has the shortest OIT, which means this sample has poor oxidation stability. This resin may need to add some additional antioxidant to enhance its stability. Well, sample C has the longest OIT, which means this resin is mostly stable against oxidation. The figure on the right side shows that copper contamination could significantly accelerate the oxidation of polyethylene. With just a small amount of copper contamination in PE, its OIT time is observed to be significantly shortened from the normal 17 minutes to less than 6 minutes at the measurement temperature. Polymers' crystallinity and crystal structure have big impact to the mechanical properties of their end-use product. Because DSC can precisely measure the crystallization and crystal melting of polymers, this technique is commonly used by processing engineers to guide their polymer processing. Here, we would like to discuss 3 examples on processing polypropylene under different conditions. This first example is processing polypropylene with and without adding additional heat treatment. The pink curve in this figure shows the melting of a regular polypropylene resin without any additional heat treatment. The red, blue, and green curves are the results of polypropylene resins that are treated at different temperatures, ranged from 110 to 120 degrees Celsius. From this DSC temperature scan measurement, we can clearly identify a second melting peak, which correlates to the melting of polyethylene. Therefore, we can conclude that this PP resin contains small amount of PE, and with an additional post-processing heat treatment, the PE phase also gets crystallized. The second example shows how much molding temperature could impact the polymer's crystallization rates. From this DSC isothermal test results, we can see that if we set the mold temperature at 120 degrees C, polymer's crystallization peak is observed at 1.2 minutes. But if we increase the mold temperature by 10 degrees, it significantly slows down the crystallization rate. The peak of the crystallization is observed at almost 16 minutes. The third example here is to demonstrate the influence of nucleating agent in polymer processing. From this isothermal test results, we can see that with adding a small amount of nucleating agent to polymer A, it can significantly accelerate the crystallization rate. The peak of the crystallization is observed to shift from 2.7 minutes down to less than 0.3 minutes. Here is an example showing the application of the real-view polarized microscope in the DSC measurement. The figure here shows a cooling curve of a semicrystalline polymer, the PVDF. The camera view allows us to be able to track the formation of crystals during cooling. Let me play the video here. As we're cooling the polymer, when the temperature is approaching 140 degrees C, which is the crystallization temperature of PVDF, we start to observe the formation of the crystals. Also, using this camera view, we can study the influence of cooling rate to the size of the crystals. From our measurement results, we can clearly see that decreasing the cooling rate could have the crystal structure forms better, and also the size of the crystals are much bigger compared to using a faster cooling rate. Using this polarized microscope with DSC measurement not only allow us to be able to monitor the formation of the crystal, it also gives us the capability to quantify the size of the crystal in the polymer. Here is another practical example showing the importance of using real-view microscope system with DSC analysis. Packaging films are commonly laminated with multiple layers. Each layer could be as thin as less than 5 micrometer. The DSC analysis in combination with using this polarized microscope allow people to be able to identify the type of polymers in each layer. This is a very interesting reverse engineering case study. Here we have a piece of unknown packaging film. Underneath the microscope, we can see that it has 3 layers. In a typical DSC temperature scan measurement, which is this green curve in this figure, we see 2 melting peaks, which associate with the melting of polyethylene and polypropylene. So we know that this film may contain polyethylene and polypropylene layers. However, the question is, which layer is what? With this question in mind, we rerun this sample under the microscope. From this video, we can see that when the temperature is approaching to the melting temperature of PE, the center layer first turns black. This tells us that this center layer is made of polyethylene. Then, as we further increase the temperature, when the temperature raised up to 150 and 160 degrees C, which is the melting temperature of polypropylene, the 2 outer layers both turn black. So from this combination testing results, we can conclude that this particular packaging film is made of 3 layers. The center layer is made of polyethylene and the 2 outer layers are polypropylene. Now, let us change subject and talk a little bit about the application of STA technique. The STA instrument can perform simultaneous DSC and TGA analysis on polymers. This technique is commonly used for polymers compositional analysis. Here is an example of using STA to measure a recycled PCR resin. Through a simple temperature scan measurement, the STA DSC part of the signal identified 2 melting peaks, which correlates to the melting of HDPE and PP. From this part of the results, we can say that this PCR batch mainly contains HDPE and PP. In the meantime, the TGA part of the analysis allows us to be able to identify the percentage of inorganic impurities. From this figure here, we can see that both PE and PP degrade at temperature above 400 degrees C. And then we switch the gas purge from using nitrogen to use air, further burn down additional carbon. After that, there are about 2% of residues that cannot decompose at the testing temperature range. So this result tells us that there are about 2.2% of inorganic impurities in this recycled plastic resin. Here is another interesting study of using TGA-STA analysis to quantify the thickness of polymer coating on drinking cans. Soda and Coke cans are made of aluminum. However, we all know that Coke or Pepsi are very acidic. The pH of Coca-Cola is reported to be only 2.6 and 2.7. So over time, they could cause corrosion to the surface of the can. In order to prevent acidic corrosion, people coat the surface of the can with a thin layer of polymer. One most important information a can manufacturer would like to know is how thick they need to coat their cans. If the coating is too thin, it cannot provide efficient protection. But if the coating is too thick, it is going to cost more money. A TGA analysis can help you to quantify the thickness of a can coating, how thick your competitor coat their cans. To find out the answer, we can cut a piece of can and load it to a TGA or STA instrument and conduct a simple temperature scan measurement. At temperature greater than 400 degrees C, we observed a small percentage of weight loss, which correlates to the decomposition of the polymer coating. So using the mass of the polymer and the can surface area, we can then calculate and estimate the thickness of the coating. Here is another example of using TGA-STA technique to do reverse engineering study and find out the formulation of a competitor's product. Rubber compounds are mixtures of multiple components, including natural and synthetic rubbers, some small molecule ingredients such as lubricating oils, and other ingredients such as cross-linking agent, colorant, inorganic fillers, or carbon black. The goal of doing rubber compounding is for the purpose of achieving certain mechanical and physical properties without overinflating the cost. A TGA-STA analysis can help quantifying the weight percentage of each ingredient group in rubber compound. The figure in this slide is a typical TGA decomposition spectrum of a rubber compound. The first 8% weight loss step here represent the composition of some small organic molecules or volatile stuff such as oil. The second weight loss step is the decomposition of the main rubber polymers. After the rubber decomposed, we switch the gas purge from using nitrogen to using air. Then the third weight loss step indicating the burning of carbon black. At the end of the test, any remaining residues are inorganic fillers. In addition to use TGA for compositional analysis, other thermal analysis techniques such as DSC, TMA, and DMA are also commonly used in rubber industries. Here is one example of using DSC to investigate how carbon black affects the thermal behavior of rubber compound. Here we have 3 rubber compounds with a mixture of natural rubber and butadiene rubber. The only differences in their formulation is the amount of carbon black. Sample A has no carbon black, sample B has 5 parts, and sample C has 50 parts of carbon black. From the DSC measurement on sample A, we can see the glass transition temperatures of natural rubber and butadiene rubber. At a slightly higher temperature, we can also observe the crystal melting of butadiene. Adding carbon black to the compound can help enhance the compatibility of these 2 rubbers. This conclusion is supported by 2 of our testing results. First of all, adding carbon black can suppress the melting of butadiene. With adding more carbon black into sample C, no melting is observed. Also, we can see that the 2 rubber glass transition temperatures are shifting toward each other. This glass transition shift can also be observed from a TMA measurement. TMA is also a good characterization technique to investigate the thermal dimension stability. Rubber material always have large thermal expansion over temperature. This could have big influence to their applications. So from a TMA measurement, we can clearly see that adding carbon black to the compound can help significantly reduce the CTE of the rubber. This is especially obvious at temperatures above their glass transition. A TMA instrument is commonly used to study a material's dimension stability over temperature. Another application example is in this printed circuit board manufacturing. The PCB board is made of glass fiber reinforced epoxy and laminated with multiple layers with electrical component and other insulations and materials. During their applications, any differences in their expansion could potentially cause cracking or delamination, which leads to the product failure. Therefore, in PCB industry, people have created a specific industry standard method of using TMA to quantify the CTE on a circuit board in all three XYZ directions. In addition to measure thermal expansion, TMA is also sensitive is also sensitive in monitor your materials thermal shrinkage. Here is a fun research of studying the anisotropic behavior of a shrink wrap. So let us peel off some labeling film from a water bottle, and then we cut two pieces of samples from both the lengthwise and crosswise directions. We load these two samples to the TMA and conduct a temperature ramp experiment. So from the measurement results, we can see that in the lengthwise direction, during heating, we can see that the sample undergoes a thermal expansion with increasing temperature. But in this crosswise direction, after the temperature passes 50 degrees C, the film undergoes a significant shrinkage. The recorded shrinkage is as high as over 70%. Actually, this anisotropic property is purposely created through film processing. This allows the shrink wrap film to be able to achieve a good attachment to the bottle. The dynamic mechanical analysis is another important technique for polymer characterizations. DMA is typically used to characterize the mechanical and viscoelastic properties of end-use products. First of all, DMA is the most sensitive instrument in measuring the glass transition and subambient transition temperatures of polymers. It is a lot more sensitive compared to use a DSC and TMA technique, especially in the case of testing the glass transition of a highly crystalline or a highly cross-linked material. TMA is used to quantify a material's mechanical strength, which is described as the storage modulus or Young's modulus. It is also used to quantify a material's elasticity, which is described as this damping factor, the tangent delta. Here is an example of using DMA to evaluate the mechanical property of a PCB board. Through a simple temperature ramp experiment, we can measure the material's mechanical property, storage modulus, elasticity change as a function of temperature. At the polymer's glass transition, storage modulus shows a significant decrease, while the tan delta shows a sharp peak. From these measurement results, it tells that this particular PCB board was initially not fully cured, because in our second temperature scan measurement, we can obviously observe an increase in storage modulus. Also, this glass transition temperature is shifted to higher temperature. Thermal analysis techniques are very commonly used in thermal setting polymer material characterizations. First, a DSC measurement can be used to monitor the entire curing process, quantify percentage of curing as a function of time or temperature, calculating curing kinetics and curing activation energy. The figure on the left side here shows the DSC thermogram of a epoxy prepreg resin. During the first heating, we can measure the glass transition temperature of an uncured resin and also quantify the exothermic curing activity. After the first heat, we cool it down and then conduct a second heat test. From this second heat measurement, we observed a big shift in glass transition temperature. No further curing activity is observed, which means this sample was fully cured through the first heating. Secondly, DMA is another common technique to study thermoset curing. A DMA measurement can quantify the modulus change of the sample from before and after curing, monitor any residual curing through the first heating, and I can also monitor and quantify the TG shift from before and after curing. In addition to that, DMA is one of a key characterization technique which allows people to calculate and estimate the cross-linking density of a thermoset material. Here is a DMA measurement results of 3 rubber elastomers, which have slightly different curing cross-linking density. Sample C is more cross-linked and sample A is less cross-linked. From this DMA temperature ramp experiment, we see that all 3 rubbers have similar E prime storage modulus at temperature below the glass transition. The glass transition temperature shows a slight increase with increasing cross-linking density. The major difference we observed from this test is the differences in their storage modulus at the temperature above their glass transition in this rubbery plateau region. The higher the cross-linking density, the higher the storage modulus. There are some literature reports saying that for an unfilled, simple structure thermosetting polymer, the degree of cross-linking can be quantified through measuring their modulus in the rubber plateau region. So the molecular weight between cross-linking networks can be calculated using this equation. Then from here, we can estimate and calculate the cross-linking density by taking the ratio of the molecular weight of the monomers to the molecular weight between cross-linking networks. DMA analysis can also be used to study the mechanical properties of anisotropic materials. Here is an example of using DMA to measure carbon fiber reinforced polymer composite. The measurement was conducted in 2 directions, perpendicular to fiber reinforcement direction and parallel to fiber reinforcement direction. The testing results show big differences in their storage modulus. The modulus measured in the vertical direction is almost half a decade higher compared to the modulus measured in parallel direction. But the glass transition temperature of the polymer matrix is not affected by fiber reinforcement. Finally, I would like to talk a little bit about time temperature superposition technique. TTS is a very useful empirical theory that is commonly used in DMA analysis to predict the properties of a material over a wide range of frequency or a wide range of temperature scale, which is way beyond an instrument measurement range. The low frequency data can be used to predict a material's behavior over a long time scale, such as years long or 10 years long, that cannot be practically achieved through a single measurement. The high frequency data helps to predict a material's behavior in a short time scale, such as high-speed impact or acoustic vibration that are beyond the instrument measurement capability. Time temperature superposition analysis is a standard feature on Hitachi Nexter software. From a typical DMA temperature sweep test at different frequencies, the Nexter software can shift the curve, calculate the activation energy, and also create the master curve reporting modulus and tan delta over a wide range of frequency. So in conclusion, Thermal analysis provides useful characterization techniques for understanding your polymer materials and ensuring the quality of your product. The applications of thermal analysis are ranged from polymer resin identification, QA/QC analysis, to troubleshooting any production issues. Different techniques such as DSC, STA, TMA, and DMA provide the measurements from different perspectives. So with this new Canon-Hitachi partnership, we are expecting to provide a better support to our polymer customers with their analytical characterizations needs. With that, I would like to end my today's talk. Thank you very much for your attention, and I will be very happy to take any questions. Thank you.
Terry, thank you. That was informative. We do have some questions. The first one is, can an STA be used as a DSC? In other words, can we have both TGA and DSC if we get your STA?
That's a good question. I mentioned that STA is a simultaneous DSC and TGA and instruments. However, the DSC part, I mentioned that it is a high temperature DSC, which means STA instruments only measure sample from ambient up to higher temperatures. So it does not have the active cooling like the DSC, standalone DSC instruments. So if you're interested to measure any material that has activities under low temperatures, what I mean is below ambient temperature, so you still need to have a standalone DSC. STA is a good DSC instrument at higher temperature, which is good for measuring some inorganic things or measuring some polymer melting temperature, identifiable for those kind of signals, but not for anything subambient.
Here's another question, Terry. Thank you. The question reads as follows. PVC has low crystal, I guess it's maybe not a question as much as a statement. You could comment on it. PVC has low crystallinity, but I cannot measure TGA on DSC so well.
Oh, are you talking about it's not good to use a DSC to measure a clear glass transition on PVC?
It sounds like they're having difficulty measuring the TG on a DSC.
That is a good question. That is a good question. Actually, I mentioned in my presentation, I said for polymers that's highly crystallized, like polyethylene, highly crystallized polymer or highly cross-linked polymer, using DSC to measure the glass transition can sometimes be challenging. Right? So here is actually another case I did not emphasize in my presentation. PVC actually has a really rigid backbone chain. So that's why sometimes without adding any plasticizer, it's hard to use DSC to identify its glass transition. The transition can be weak, can be very broad, and sometimes can also associate with a big enthalpic recovery. So in this case, what you can do is consider to use a slightly larger sample size with a faster heating rate, like a 20 C a minute. And in addition to that, actually using a DMA can be a much better technique in order to precisely identify the glass transition of PVC. So PVC without adding plasticizer, yeah, sometimes there is a challenge to use DSC identify its glass transition.
Thank you. I want to remind the audience, if you have a question, put it in the QA. We have 5 minutes. There's 2 questions, but we certainly at 12 noon we'll end our discussion. But if you have others, we will get back to you individually if we don't cover them in the next 5 minutes. Next question, can I calculate cross-link density of a biopolymer hydrogel?
Oh, that's a good question. Can we calculate? The answer is probably not. In my presentation, I mentioned that a lot of literature, they said, yes, using DMA, you can quantify the cross-linking density, but that's mainly limited to what they say is something like a simple polymer structure. And hydrogel that you have 90%, hydrogels are water. So it is a complicated system. So in this case, it is hard to really use this method to calculate, to quantify the cross-linking density. However, that doesn't mean that you are not able to use this measurement to get a relative comparison, which means if you have two hydrogels, one is more cross-linked, one is less cross-linked, with the exact same formulation, okay, you can still use this technique to do relative comparison. The higher the modulus you measured, in general, you can estimate that this particular hydrogel has higher cross-linking density. That's based on the fact that they have the same concentration, exact same formulation.
Thank you. The last question we have, again, folks, if you have any others, please submit them in the Q&A, is can we use STA to quantify how much polyethylene and polypropylene are in PCR? I guess that's post-consumer recycled material. In your slide, you have one example of PE and PP.
Yes. In my presentation, I did have a slide that's saying that using STA, I can identify PE and PP or identify polymer types using a simple STA temperature scan measurement, right? However, if you really want to quantify, okay, if you have a PCR resin, you want to quantify how much polymers, resins in the components, in the whole component, I would highly recommend use a DSC instead of STA. Because a DSC, actually, you can precisely quantify by measuring their crystal melting activity, integrating the melting area, you can actually do the calculation. It's a more precise way to quantify the amount, the percentage of different polymers in PCR resin. DSC is more accurate compared to use STA method.
Okay. There's a question, Terry, that just came in, and maybe we'll make this the last one for now. Bear with me. It says, is the MDSC signal present on STA?
Yes, that is correct. For Hitachi instruments, the STA instrument is fully integrated with the modulated feature. You can do modulated measurements. You can do modulated TGA, modulated DSC on your STA instruments as well. That is correct. You can.
Okay. Okay, seeing no other questions, I want to thank you for your time. We respect your time. One more quick question that just came in. How would you recommend to analyze a mixture of a small chemical entity, an API, active pharmaceutical ingredient, with thermoplastic polymers such as EVA or silicone elastomer? How would you recommend to analyze the API with the thermoplastic polymer?
That's a good question. How do we do that? If I get an unknown polymers or unknown materials for the analysis, the first thing I will do is I will load the sample on the STA or TGA. What I'm measuring is like roughly get a quick and dirty scan on seeing like how much moisture do I have, roughly what kind of material it is, and what most importantly, what is their degradation temperature. So this helps me to have a good idea regarding how do I design the next measurements. So after I do the TGA measurement, find out at what temperature the samples start to become not very thermally stable, in this degradation temperature, I will design my DSC measurement condition to stay below under that temperature. So then the next test I will do is I will use a DSC measurement method to identify the sample. First of all, I will go from the lowest temperature I can reach and then scan it all the way up to the temperature before the sample starts to degrade. From this temperature scan, I may also do heat-cool heat. So what I can identify is, am I able to see some glass transition? Am I able to see some melting? From that, you can identify the API, identify what other polymers you have in there, and also whether or not, you can, if the system is way too complicated, you can also consider to do modulated DSC. So you're modulating, and then you can separate different activities so that you can get a better, clear picture of what's inside. So just in summary, this is what I will do. When I get an unknown material, the first thing I do is I will load the sample to a TGA or STA, measure the sample thermal stability, and see some quick and dirty information. Then I load this sample to a DSC. Start from the lowest temperature your DSC can do and heat it up to all the way before the sample starts to degrade. From this measurement results, you can get a full picture of what's inside. Thank you.
Terry, thank you again, and thanks to the participants for coming in. We do appreciate your time. Two things, you could email questions to the email address there, tchen@canoninstrument.com, and Terry will get back to you directly. And this presentation will be on our website. There will be a link there so you could access it and share the content. Thank you all for attending. Have a nice day.
Thank you, everybody.